So for today's lesson, we'll be talking about the basic uses of modular arithmetic and some more advanced uses. We'll assume that everyone here has a basic understanding of what a modular congruence is. If A is congruent to B mod n, then A and B differ by a multiple of n. So other than that, I don't think any prerequisites are necessary. So we can get started on the first topic for today, which will be the Chinese remainder theorem. So the Chinese remainder theorem is a theorem that lets us collate several congruences into a single congruence. So what this means is that suppose that we have several pairwise relatively prime positive integers. So pairwise relatively prime means that no two of them share any common factor greater than 1. Well, if we define bi to be any arbitrary positive integers, we consider the system of congruences. X is congruent to B1 mod A1 and on to Bn mod An. So essentially, we have a system of n congruences, and the moduli of these congruences are all relatively prime. Then, what the Chinese remainder theorem tells us is that we can take this system of congruences as a single congruence modulo the product of A1 through An. The system of congruences is equivalent to a single congruence. X is congruent to k modulo the product for some integer k. Note that we don't actually know what k is. It just tells us that it exists. So if we know what x is modulo A1, modulo A2, and all the way to modulo An, then there's only one possible value for x modulo the product. And as this mentioned earlier, the theorem doesn't actually tell us what k is. So if we want explicit information on exactly what congruence the system of congruences simplifies to, then we'll need to do extra work. But if we just need to know that it exists or count how many solutions there are, then the Chinese remainder theorem tells us that we just have to consider the modulo the product. Does anyone have any questions about the statement of the theorem? If not, then let's get started on the first problem for today. So we'll be looking at this problem from the 2012 AMY. I'll give you a bit of time to read over the problem and think about it. So is everyone clear on the statement of the problem? Let's get started on it. So we want to find the number of positive integers up from 1 to 10,000, which are all simultaneously 7 safe, 11 safe, and 13 safe. So does anyone have any ideas on how to start approaching this condition? Feel free to type in chat. So what this means is that what p-safe means is that n is more than 2 from the nearest multiple of p. So you can say that 4 is 7 safe because the distance from 4 to the nearest multiple of 7 is 3. But say 9 isn't going to be 7 safe because 9 is 2 away from the nearest multiple of 7. So I see some ideas here where we're trying to split the condition into the 3 conditions, 7 safe, 11 safe, and 13 safe. So when is n 7 safe? Well, n is 7 safe when it is 3 or 4 mod 7. If it's 2 mod 7, then it's too close, and same for all the other residues. It has to be 3 or 4 mod 7. And likewise, if it's 3 or 4 mod 7, then it's far away from any multiple of 7, so it's going to be safe. What about n for when is n 11 safe? Well, n can be 3, 4, 5, 6, 7, 8. Again, if it's, say, 10 mod 11, that's too close to a multiple of 11. So for these 6 residues, it's far away enough. And with the exact same logic, we conclude that n is 13 safe if and only if n is one of these 8 residues mod 13. Does anyone have any questions so far? Okay, let's move on. So we've now found individually when n is 7 safe, 11 safe, and 13 safe. But our condition is that n has to be safe modulo all of these integers simultaneously. So what can we do? Well, since 7, 11, and 13 are relatively prime, they're prime numbers, that by the Chinese remainder theorem, this allows us to consider mod 7 times 11 times 13, which happens to be 1001. So we can first choose what n is modulo 7, then we choose what it is modulo 11, then we choose what it is modulo 13. And then the Chinese remainder theorem tells us that it gives us a unique residue modulo 1001. So from what we have earlier, there are 2 residues that we can choose mod 7. There's 6 residues we can choose mod 11, and 8 that we can choose mod 13. So the number of ways we can choose mod 1001 is the product of these. The modulo, the different primes are independent. So we can just multiply the number of ways, and we get 96 residues mod 1001. So what we want is the number of n from 1 to 10,000 that work. Well, since we know that 96 residues mod 1001 work, we know that 960 numbers from 1 to 10 times 1001 will work. So we're close, but we might be overcounting. We know that there's 960 numbers from 1 to 10,010 that are safe. But we only want the number of numbers that are from 1 to 10,000 that are safe. So we need to get rid of ones that are in this of working n in this interval from 960. So what are they? I'll just say right now, they're 10,006 and 10,007. So you can check this using the fact that 10,010 is divisible by 7, 11, and 13. So the nearest multiple of 7 is 10,003. The nearest multiple of 11 is 9,999. And the nearest multiple of 13 is 9,987. And you can just use these close multiples to cancel out, to rule out any of the other possibilities and verify that these ones work. So we subtract that and we get the answer. So first, using the Chinese remainder theorem, we found that there are 960 integers from 1 to 10,010 that work. But we only want the number of integers from 1 to 10,000 that work. So we need to, so we're overcounting. We need to subtract the number. So when I say integer works, I say that because it is safe, 7 safe, 11 safe, and 13 safe. So we know that 960 numbers from 1 to 10,010 are safe modulo all three of these integers. But we only want the number from 1 to 10,000. So we're going to have to subtract the number. We're going to have to subtract the number of integers from 10,001 to 10,010 that are simultaneously 7, 11, and 13 safe, because we overcounted them. Any other questions? If not, then let's move on to our next example. We have another problem from the Amy. I'll give you a bit of time to read over this. Okay, does everyone understand the premise of the problem? So we get to pick 3 different choices of m, 2, 3, and 5. So let's just track each of them individually. So we see that the condition is this equivalent to a sub n plus m is congruent to a sub n mod m, because m has to divide the difference between the two. That's what the given condition is. So if we pick m equals 2, we see that a sub any odd integer is the same and a sub any even integer is the same. Is this step understandable? So we know that the AI have to be a permutation of 1 to 30. So what this tells us is that 15 of the AI are odd and 15 of them are even. But we know that A1, A3, and so on all have to be the same parity. Same with A2, A4, and so on. So either all the so either A1, A3 through A29 are all odd, and the A sub even is even, or A sub odd is even and A sub even is odd. So we have 2 ways to make this decision. So let's move on to m equals 3. When we have m equals 3, then we see that a sub 1 mod 3 is constant, a sub 2 mod 3 is constant, and a sub 0 mod 3 is constant. Does anyone have any questions thus far? Okay. So by 2 ways, what do we mean by 2 ways when we pick mod 2? So you can either choose all of A1 through A29, A1, A3 through A29. So basically, 15 of them have to be even and 15 of them have to be odd. So either these 15 are even and the other 15 are odd, or the other 15, or these 15 are odd and the other 15 are even. So we're only considering mod 2. 15 of them have to be 0 mod 2 and 15 of them have to be 1 mod 2. So basically, what this okay. So how do I get three sequences mod 3? So if you just take a look at the second bullet, at the second bullet here, a sub n plus 3 is equivalent to a n mod 3. So we know that 1, 4, 7, 10, so on have to be the same. 2, 5, 8, 11 have to be the same, and then 3, 6, 9, so on have to be the same. So now 10 of the AI have to be congruent to 0, 10 are 1, and 10 are 2 mod 3, because they have to be a permutation of 1 through 30. So this gives us 3 factorial ways to choose the residues mod 3. You can either make A1, A4, A7, so on, all 0, 1, or 2 mod 3, and then you have 2 choices for the other 2. And finally, for m equals 5, we get 5 chains of congruences. The indices are either 1 mod 5, 2 mod 5, 3 mod 5, 4 mod 5, or 0 mod 5. So by the same logic, we get that one of these chains is 0 mod 5, one of them is 1 mod 5, and so on. So there's 5 factorial ways to choose the residues mod 5. So where did A2, A3, A4 go? I just left them out for space reasons. So there are actually 5 chains of congruences here, but because they all look the same, I just omitted them. So now suppose that we've chosen residues for each AI mod 2, 3, and 5. If we fix x mod 2, x mod 3, and x mod 5 by the Chinese remainder theorem, that determines its unique value x mod 30. But the AI are only allowed to be from 1 through 30. So once we choose x mod 2, 3, and 5, then it fixes what x should be. So once we've chosen what the sequence looks like mod 2, mod 3, and mod 5, every term of the sequence is uniquely determined. But we're not done yet. It might be possible that this sequence isn't a permutation. If 2 terms are equal, then it's not a permutation. And if no 2 terms are equal, then it's a permutation. So let's check when it can be a permutation. Well, suppose that two terms are equal. AI and AJ are equal. Well, I has to be equivalent to J mod 2. Because if they're different parities, then A sub I and A sub J have to be different parities by the way we chose. Does anyone have any questions so far? Yep, parity is odd and even. And the question told us that the A1 through A30 is a permutation of 1 through 30. So that's what I mean when I say permutation. So if I is congruent to J mod, so by the same reasoning, I has to be congruent to J mod 3 if AI equals HJ. Because if I wasn't congruent to J mod 3, then AI and HJ can't possibly be congruent mod 3. Similarly, mod 5. By the Chinese remainder theorem again, we know that I and J have to be the same mod 30. But that tells us that I equals J because I and J are restricted to be from 1 through 30. What this means is that once we've made the choices mod 2, mod 3, and mod 5, then that defines a unique sequence, and this unique sequence is guaranteed to work. That means we just have to find the number of ways to choose modulo 2, modulo 3, and modulo 5. We mentioned this earlier. There's 2 factorial ways mod 2, 3 factorial ways mod 3, and 5 factorial ways mod 5. And when we multiplied them, we get the total number of ways to choose the sequence. And for answer extraction, we only take the last 3 digits. Does anyone have any questions? So why do we need to prove I equals J? We need to verify that the sequence is a permutation. It's the numbers 1 through 30 in some order. And to prove this, we just need to check that no two terms are equal. So we just consider, suppose that two terms are equal, a sub I and a sub j are equal. Well, then we prove that they're actually the same term. So no two terms are equal. No two distinct terms are equal. Yep, so we're essentially using proof by contradiction here. If there aren't any other questions, then we can move on to the next segment of, could you put the question back in? I don't have control of the screen. Yep, thanks for the problem source. You could also note that down and take a look after class.
All right, so now we're going to be discussing Euler's totient function. So to do that, first I'll define this function, and then we'll discuss the related theorem. So the totient of n is defined to be the number of positive integers less than n that are relatively prime to n. And so this might seem like sort of conceptual definition, but we can also provide like a mathematical formula for evaluating it. So if n has distinct prime factors p1, p2, all the way to pk, then phi of n is defined to be n times n times like 1 minus 1 over p1 times 1 minus 1 over p2 all the way to 1 minus 1 over pk. And we can also like, so to show this formula, one way is to note that the probability that an integer is divisible by the prime p1 is 1 minus 1 over p1. So so like to find the probability that some random integer is relatively prime to n is the probability that it's not divisible by any of its primes. So that total probability would be this product here. So then if we multiply it by the number of integers that we're considering from 1 to n, that's how we get that formula. So now we can move on to the main theorem. And so we have, if a is a positive integer relatively prime to n, then a to the phi of n is 1 mod n. So does anyone have any questions so far? We're going to go through a proof of this theorem next. All right, so I'll just quickly go through the proof. So if we consider S to be the set of residues mod n that are relatively prime with n, then then after that, we can consider another set T, which is formed by basically taking every element of S, multiplying it by A, which is some positive integer relatively prime to n, and then computing that mod n. So one thing nice about this is that all of the elements of T are still going to be relatively prime to n, because both A and S are relatively prime to n. But another thing that we claim is that all of these, that T basically has all of the same elements as S. And to show this, we can show that this map from S to T is an injective map. So that's if we have, so that means if we have distinct elements S and S prime in S, then AS is not equal to AS prime mod n. So basically, all the elements of S are mapped into distinct elements in T. And to show this, we can use contradiction. So if we suppose that AS equals AS prime for S not equal to S prime, since GCD of A and N is 1, we can just divide this modular congruence by A, and we get S equals S prime mod n, which is a contradiction. So that means that all of the elements of S are mapped to different elements in T. So this means that both S and T have the same number of elements. But since we said earlier that all of the elements of T are relatively prime to n, that this means that S has to equal T, because S was also the set of residues that are relatively prime to n. So we can conclude that they both have the same elements. But the more interesting thing here is if they have the same elements, then the product of the elements is also the same. And if we take the product of all of the elements in S, we just get this product of S for S in capital S, but this is equal to the product of the elements of T, which if we consider this mod n, this is A is the product of AS, where S is in capital S. And since there are phi of n elements in S, we can factor out the A. And so this is equal to A to the phi of n times this same product of the elements in S. And since all of these elements in S were relatively prime to n, we can divide them out, and we just get A to the phi of n is 1 mod n. So does anyone have any questions here? Okay, so there's another thing for primes. So for Euler's totient function, if we plug in a prime number, we get an even simpler theorem that says if you have a positive integer a that's co-prime to p, then a to the p minus 1 is 1 mod p. So this is just a direct result of Euler's totient theorem at when you plug in n as a prime. But it's important because it's like a lot simpler form than 5n. So with that, we'll move on to our first question in this section. So take a few minutes to think about this one. Okay, so let's get started. So does anyone have any ideas for how to start here? Okay, so I think a few people are hinting at this, but no one said it directly. But the first thing here is that the floors are not very useful. So like we want to try to get rid of the floors so that we can just make it a regular sum. So so that means that to get rid of the floors, we need to get the remainder when all of these when like a to the p is divided by p. So this means that so from Fermat's little theorem, we know that a to the p is a mod p. So if we subtract a and make it a to the p minus a and divide that by p, that will be an integer. So that's actually going to be the floor. So with that, we can rewrite our entire sum like this. So this is the sum from a equals 1 to p minus 2 of a to the p minus a over p mod p. Also, I'm going to be writing everything in terms of p until the end. Yeah. Okay, so someone said this before, but to compute this mod p, if we multiply everything by p, then we really need to find this sum from a equals 1 to p minus 2 of a to the p minus a mod p squared. So we're just multiplying everything by p to get rid of the fractions. So so now does anyone have any ideas for how to evaluate this sum? So I think one idea someone said was to factor out a and then write it as a to the p minus 1 minus 1. But the reason this is not very useful is that we're working mod p squared. So if you wanted to use something like Euler's totient, you need like an exponent close to a to the phi of p squared, which is a to the p times p minus 1. And right now we only have a to the p minus a, so that's not going to be very helpful right now. Does anyone have any other ideas? Okay, so we sort of yeah, so I think Alex has the idea. So here if we use Euler's totient with mod p squared, it doesn't appear to be helpful. But something that we could do is try pairing the terms a and p minus a. And the reason we might try something like this is to see if something would cancel. And in this case, it does, because if we expand p minus a to the p with the binomial theorem, it starts out like p to the p minus p choose p minus 1, p to the p minus 1a, plus like a bunch of other terms. But since p is an odd prime number, the last term we know has to be minus a to the p. So that cancels out the a to the p from the beginning. So then we end up with this sum. And here, every term is divisible by p squared. We can see that for all of these terms, and then note that p choose 1 is p, so it's p times p, which is p squared. So all of these terms have a factor of p squared, so this whole sum is 0 mod p squared. So if we pair up the terms, if we pair up these to get 0 mod p squared, then how many pairs can we, so if we do this for, so now if we actually add the two terms, accounting for the minus a term, first a to the p plus p minus a to the p is 0 mod p squared. And then you have minus a minus p plus a. So that all comes out to minus p mod p squared. So now how many pairs do we have here? Remember that we were summing from 1 to p minus 2. Yeah, I think that's right. So first, a equals 1, if we plug that in, we just get 0. And then the remaining terms, we can pair them up. So we can pair up the term for a equals 2 and a equals p minus 2, a equals 3 and a equals p minus 3, and so on. We can pair up all of these terms. And since we have p minus 3 terms remaining, we end up with p minus 3 over 2 pairs. And so now, since each of these pairs had a sum of negative p, if we multiply that out, we get negative p times p minus 3 over 2. And this is equivalent to p times p plus 3 over 2. The reason for this is I just added p squared to negative p times p minus 3 over 2. So these two are equivalent mod p squared. And now remember that our final answer was to determine the sum of a to the p minus a over p mod p. So then this comes out to p times p plus 3 over 2 divided by p, which is p plus 3 over 2 mod p. So plugging in p is 2017, we get 1010. So does anyone have any questions? Yep. Sure. So if there are no other questions, we'll go to our next problem. So take a few minutes to think about this. So does anyone want to say some ideas for getting started? Yeah, I think we will look at cases eventually, but I guess it's not so clear what the cases are um, without doing anything in advance before that. So does anyone see anything that you can do immediately from this equation? Yeah, so we'll use Joshua's idea to take mod P and mod Q. And by this, we would want to try to apply Fermat's little theorem. So note that if we take so first we'll assume that P is greater than or equal to Q because the equation is symmetric. But then if we take 5 to the P minus 2 to the P mod P, 5 to the P is 5 mod P by Fermat's, and 2 to the P is 2 mod P. So then it just comes out to 5 minus 2, which is 3 mod P. And similarly, 5 to the Q minus 2 to the Q is 3 mod Q. So now I think some of you said this in the chat, but first, neither of them can be equal to 2. And so we see that Q equals 2 doesn't work. And that would be due to parity reasons, right? Because 5 to the P minus 2 to the P is going to be odd, and 5 to the Q minus 2 to the Q is also odd. So PQ cannot be even. So Q can't be 2. So now the next natural thing is, what about Q equals 3? And because of what we've written here, this appears nice because we know that 5 to the Q minus 2 to the Q is 3 mod Q. So if Q equals 3, then Q divides 5 to the Q minus 2 to the Q. So now the question is, which values of P work? And remember that we assumed P is greater than or equal to Q. Two doesn't work because of parity, right? Because 5 to the P minus 2 to the P is going to be odd, and 5 to the Q minus 2 to the Q is also odd. So that means that whole product is odd, but if Q is even, how can Q divide something that's odd? So does anyone have ideas for what values of P work? Remember that we're setting Q equals 3 here. Yep, so P equals 3 clearly works because it's for the same reason that Q equals 3 works. But yeah, so P equals 13 also works. And the reason you would see this is if you let P be greater than 3, then 5 to the P minus 2 to the P, we already said this was 3 mod P. So if P is greater than 3, P cannot divide 5 to the P minus 2 to the P. So that means since P has to divide this product, it has to divide 5 to the Q minus 2 to the Q. But we already said we're setting Q equals 3. So then if we know that P divides 5 to the third minus 2 to the third, which is 117, then we can say exactly what P is. So 117 is 9 times 13. And since we already accounted for P equals 3, the only other solution is P equals 13. So now with that, we can move on to assuming that Q is greater than 3. So we're assuming P is greater than or equal to Q, which is greater than 3. So now does anyone have any ideas for how to start with this case? So if we just look at what we wrote here, that 5 to the p minus 2 to the p is 3 mod p, and 5 to the q minus 2 to the q is 3 mod q. And if both p and q are greater than 3, that means that p cannot divide 5 to the p minus 2 to the p, and q cannot divide 5 to the q minus 2 to the q. So that means that we have q has to divide 5 to the p minus 2 to the p, and similarly p has to divide 5 to the q minus 2 to the q. So if q divides 5 to the p minus 2 to the p, then we must have that 5 to the p is equivalent to 2 to the p mod q. But we also know from Fermat's little theorem that 5 to the q minus 1 is equivalent to 2 to the q minus 1 mod q. So does anyone see any way we can sort of combine these two equalities to get another relation? So when I mean to combine, I mean like if I were to multiply some power of 5 to the p by some power of 5 to the q minus 1 and trying to get another equation from that. Yeah, so we can combine these to get 5 is equal to 2 mod q. And the way we would do this is first, we note that GCD of p and q minus 1 is 1. The reason for this is that we're assuming that p is greater than or equal to q. So that means that p is greater than q minus 1. So if you have a prime p that's greater than some integer q minus 1, obviously q minus 1 is not divisible by p, so their GCD is 1. And because they have a GCD of 1, we can find integers a and b such that a times p plus b times q minus 1 is equal to their GCD, which is 1. So then if we write 5 to the ap plus b times q minus 1 as 5 to the p to the a times 5 to the q minus 1 to the b, and we substitute 5 to the p is equal to 2 to the p, and 5 to the q minus 1 is equal to 2 to the q minus 1. And simplified, this is just equal to 2 to the AP plus B times q minus 1. So since this is equal to 1, we just get 5 is equal to 2 mod q. But we're assuming that q is greater than 3. And so we get a contradiction directly. So that means that there's no more solutions, and our only solutions were these. Does anyone have any questions? We're going to have a short break after this for 5 minutes.
We're gonna start again. And our next topic of the day is gonna be orders. So from Fermat's little theorem in the last section, we know that a to the p minus 1 is equivalent to 1 mod p for any a not divisible by p. But a big question is, do we always need to raise a to such a high power in order to get 1? In particular, FLT tells us that 2 to the 6 is equivalent to 1 mod 7, since 6 is 7 minus 1. But in fact, 2 cubed also works. So 3 is obviously less than 6. So one might ask, how small can we get for certain residues? And motivated by this question, we can now define the order of A mod P to be the minimum exponent E, such that 2 to the E is equivalent to 1 mod P. And E will be denoted as the order of P mod A. I mean, the order of A mod P, ord P A. So we know that this definition is good because order always exists, since by FLT is at most P minus 1. So let's go ahead and prove some properties about order. So the first relation we have regarding order is order divisibility, namely that if a to the k is equivalent to 1 mod p, for prime p and p does not divide a, then the order of a with respect to p divides k. Order is the minimum exponent of a, such that a to the e is equivalent to 1 mod p. Okay. There's a small typo here. It should say a to the e equivalent to 1 mod p, not 2 to the e. But yeah, order is defined to be the minimum exponent such that it's equivalent to 1. So let's go ahead and prove this property. So first, let's denote e, the order as e. So which r satisfy a to the r is equivalent to 1? Obviously e does. Can we name some other easy ones which also satisfy this? Yeah, sure, all multiples of e. So we're gonna go ahead and choose a convenient multiple of e. This is very similar to what Aditya did in the previous question. Consider the multiple of e, ne, a to the ne, where ne is less than or equal to, oh, that should say n plus 1 e, another typo. So it should say ne is less than or equal to k is less than n plus 1 times e. So then we know that a to the ne is equivalent to a to the k is equivalent to 1 mod p. So now we just divide both sides by n times e. I mean a to the n times e. So a to the n times e minus k is equivalent to 1 mod p. So why is this good? Oh yeah, and somebody asked, why do we use e? E stands for exponent. Like, because order begins with O, but O's look ugly, I guess. So, oh, that is another typo. It should say a to the k minus ne, not a to the ne minus k. It should say a to the k minus ne. This ends up not mattering, but it keeps things positive. So anyways, yeah, the next bullet also has the same typo. So we know that k minus ne is less than e since how we defined n times e. So in fact, k minus ne is going to be the remainder when k is divided by e. So it has to be less than e. So now by minimality, k has to be equal to ne. That is another typo. Wait, no. Yeah, that's fine. So k has to be equal to ne. Since this quantity is less than e, but e is minimal. So that means this quantity has to be 0. Okay, so e was defined to be the minimal number such that a to the e is equivalent to 1. But we just found that a to the k minus ne is also equivalent to 1, which means that, and since k minus ne is less than e, this seems to be a contradiction, but e was defined to be the smallest positive number such that it's greater than, such that a to the e is equivalent to 1. So this means that k minus ne has to be 0. So k equals ne. So for clarity, I'll type in the chat, it's supposed to say k minus ne, and ne is less than or equal to k is less than n plus 1 times e. So does this proof make sense? So in simple terms, the property says that if a to the k is equivalent to 1, then the order divides k. So this is the most basic property of orders. And something to note is that this just means that the order always divides p minus 1, since by Fermat's little theorem, a to the p minus 1 is equivalent to 1 mod p. So the only possible orders for any number a are just the divisors of p minus 1. So now this is a very simple property, but using it, we can get a ton of interesting stuff about orders. So in particular, no, the order is not the smallest factor of k, is not the smallest divisor of k, is e. Like, we just know that e divides k. Like, for all we know, k is equal to e. And the supposition is still true. So now let's get into some more interesting properties about orders. So it's natural to ask if Fermat's little theorem is tight. Namely, do there exist a with order equal to p minus 1? So somebody asked, how do we find e? So orders are very tricky to find in general. We can find a ton of properties about them, but it's really hard to actually find order. So that's why, for the most part, we generally like to use FLT instead of finding the order of numbers. Yeah, so basically we don't unless the numbers are special, but orders can give us a lot of insight into questions. So anyways, we just saw, like, for example, when a equals 2 and p equals 7, that 2 cubed suffice. The order was 3. So the natural question is, do there exist numbers with order equal to p minus 1? So the answer to this question is actually yes. So for any prime, there always exists a such that a to the p minus 1 is equivalent to 1, and no k less than p minus 1 satisfies a to the k is equivalent to 1. And such a are known as the primitive roots of p. So let's go ahead and prove this. This is sometimes called Gauss's lemma. So we want to prove for any prime p, there exists a residue with order p minus 1. So this proof is going to be a bit involved. We're going to start with a lemma called Lagrange's theorem, which states that a polynomial p of x has at most degree of p roots modulo p. So this theorem intuitively makes sense because it's true for the reals. So can anybody tell me why it's true for the reals though? Feel free to type in the chat. So what I mean by true for the reals is just cross out the modulo p part. Yeah, sure, the fundamental theorem of algebra. In particular, we can say that if p of x has the roots r1, r2, all the way to rn, then it can be expressed as some constant times x minus r1 times x minus r2 all the way to x minus rn. It can be factored as n different terms, which means that its degree is at least n. So that means it has to have at most degree p roots. So the general idea we want to try is to somehow factor p of x modulo p. And in fact, we can. So consider a root of p of x. Let's call it r. So here, a root means that p of r is equivalent to 0 mod p, not necessarily equal to 0. So what happens when we divide p of x by x minus r? So here we're working entirely in mod p. Yeah, sure, there's no remainder. So when we're working in modulo p, the division algorithm of polynomials still works. So we're going to have something of the form p of x is equivalent to q of x times x minus r plus c. And since r is a root, c has to be 0. So this means that p of x is equivalent to x minus r times q of x mod p. And now we're just done because we finished by induction. If there are any more roots, they have to be roots of q, and then q can be factored again. We get another polynomial q2 and continue factoring until there's no more roots. And every root generates a different linear term, and we can't have more linear terms than the degree. So we have to have that p of x has at most degree p roots. Does this make sense? So using this theorem, we can now begin to prove Gauss's lemma. It seems easy, but it's actually going to end up being very powerful. So using this theorem, we can actually prove that x to the k has exactly k roots when k divides p minus 1. So first consider x to the p minus 1 minus 1. How many roots does this polynomial have? So this is just Fermat's little theorem. It has p minus 1 roots because 1, 2, 3, all the way to p minus 1 are its roots. So what happens? So since k divides p minus 1, we can factor x to the p minus 1 minus 1 as x to the k minus 1 times q of x. So now how many roots does the right-hand side have? Yep, the left-hand side has p minus 1 roots, so of course the right-hand side also has p minus 1 roots. But what does our lemma tell us? Our lemma tells us that the first term has at most k roots, and the second term has at most p minus 1 minus k roots, since that's the degree of q. So the right-hand side has at most k plus p minus 1 minus k is equal to p minus 1 roots. but we know it has exactly p minus 1 roots. So the only way this can be true is if both inequalities are strict, which means that x to the k minus 1 has exactly k roots. Does that make sense? Great. So now we're ready to finish. Denote n of e to be the number of residues with order e for all e divides p minus 1. So first of all, what can we say about the sum of all n of e? If we sum over all possible values of e, that is. Feel free to type in the chat. So remember that we're summing over all possible orders, and every single number has an order. So the sum over all n of e should just be p minus 1, since we're counting every single number once, right? Like if a is between 1 and p minus 1, and a has order k, then a is counted in n of k. And since every single a has its associated order, when we sum over all counts of, when we sum over all n of e, we're just going to count every single number between 1 and p minus 1 exactly once. So does this sum remind you of anything? In particular, we actually talked about a very similar sum during our number theoretic sums unit. Does anyone have any ideas? In other words, what function can we substitute for n to make this true? So this was actually a homework question. The answer is the sum of e divides p minus 1 of phi of e is always p minus 1, where phi is the Euler totient function. So in the end, we want to somehow show that n is actually just the totient of e. So let's keep this in the back of our minds for now. So can anybody tell me what the roots of x to the k minus 1 are? In particular, which a satisfy a to the k is equivalent to 1 mod p? Of course, k divides p minus 1. No, this is modulo p, so they're not roots of unity. So remember we had a lemma about this. If a to the k was equivalent to 1 mod p, what did that tell us about k? Yeah, k is a multiple of the order. So with this in mind, what does this tell us about the roots of x to the k minus 1? It tells us that every single one of them has an order which divides k. So they are exactly the residues with orders which divide, that's supposed to say k, which divide k. So sum of e divides k of n of e is going to be, on the left-hand side, this counts all the roots of x to the k minus 1. And we already know that x to the k minus 1 has exactly k roots. So we know that sum of e divides k of n of e is equal to k. So remember, k is an arbitrary divisor of p minus 1. So using this relation with k at every single divisor of p minus 1, we can actually uniquely determine n of e. And we do this just by, for example, k equals 1 gives n of 1 is equal to 1. And then you consider the next smallest divisor of p minus 1, it's 2, and then so forth and so forth. And every time you consider this relation for a different value of k, we're going to get a new value of n. And once we consider this relation for all divisors of k, we can uniquely determine n of e. So this means that n of e is a well-defined function. But we already have a guess for what n of e is. N of e can be phi of e. If we plug in phi of e for everywhere where n of e is, all our relations are true. And since these relations uniquely determine n, this means that n actually has to be phi. So that means n of e is equal to phi of e for every single e divides p minus 1. So now we're done. All the primitive roots are part of the set n of p minus 1. And we know that n of p minus 1 is equal to phi of p minus 1, which of course is at least 1. So we have at least one primitive root. In fact, we have phi of p minus 1 roots, primitive roots. So that completes the proof. So this was really long. Are there any questions? Okay, great. So some people are saying they're lost, so I guess we can summarize our main points of this proof. So we wanted to prove that there exists a primitive root with modulo p. So the first thing we do is that we show that any polynomial has at most degree p roots. After we prove this, we can get that x to the k minus 1 has exactly k roots by using our inequalities from Lagrange's theorem. So now that we have this, we can start writing relations involving the roots of the x to the k minus 1. In particular, x to the k minus 1, all its roots have orders which divide k, which means that if we sum over n of e for all e dividing k, we're going to get the total number of roots, which is equal to k by Lagrange's theorem. So once we get this holds true for every single divisor of p minus 1. So now we get d of p minus 1's equations, and we can easily solve these equations to get a unique set of values for n of e. So we know that n of e is uniquely determined. We don't know what it is yet, but we know that phi of e is a valid function. And since n of e is uniquely determined, phi has to be the unique function. So we know that n of e is equal to phi of e for every single value. In particular, n of p minus 1, which is the number of primitive roots, is equal to phi of p minus 1. So those were the main steps of our proof. This proof is also inside our handout and will be in the posted transcript. So if you still have any questions, you can read it after class. And yes, remember, this proof also tells us that there are exactly phi of e residues with order e. So yes, besides primes, there are other numbers guaranteed to have primitive roots. In fact, we know that they are exactly all prime powers and 2 times prime powers, as well as 2 and 4. Yeah, phi is the Euler totient function. So let's move on with our first example. This is from last year's Amy. So find the least odd prime factor of 2019 to the a plus 1. I'll give you a few moments. And feel free to type any ideas in the chat. Yep, it looks like a lot of people already have ideas in the chat. So let's just get started immediately. So if P divides the number 2019 to the 8 plus 1, we can say that 2019 to the A is equivalent to -1 mod P, which means that 2019 to the 16 is equivalent to 1 mod P. So the order E has to divide 16. So what do we know the order is? We know it divides 16, but can we say anything else about it? So people are jumping ahead slightly in the chat. We actually first need to find the order in order to say that 16 divides P minus 1. But yeah, 16 is the order. And an easy way to see this is that if the order is anything less than 16, then the order has to divide 8, since 16 is a prime power. And we know that if the order divides 8, then we would have had 2019 to the 8 is equivalent to 1 mod P. But it was equivalent to -1, so that's impossible. So E has to be 16. And by our handy lemma from before, that tells us that 16 divides P minus 1. So now we can check primes of this form. And since this is Amy, we know that we should be able to just do it by brute force by now. So just check, 17 is not, and 97 is the next prime, which is 1 mod 16, and it ends up working. So the details are rather uninstructive, but you can just just consider it mod 17 and simplify, and you'll get it to be 1 mod 17, but -1 mod 97. 2019 to the 8, that is. Yep, this was a very easy number 14 if you knew about orders. So are there any questions? Or can we move on? So I guess let's go to the next question. This is from HMMT 2016, and I'll give you a few moments to read it. Okay, so do we have any ideas? Yeah, sure. So we only have to consider when n is relatively prime to 2010. I mean to 210, or else C of n is just going to be 0. So note that n to the Cn minus 1 is divisible by 210 looks a lot like our scenarios from before. But what's different here is that 210 is not a prime. So C of n is sort of, okay, C of n is sort of the order of n mod 210. That's supposed to say mod 210. However, 210 is not prime. So how can we fix this? Yep, so instead of looking at a mod 210, we look at a mod 2, 3, 5, and 7, and then use Chinese remainder theorem. So in particular, if we call Wn, Xn, Yn, and Zn the orders of n modulos 2, 3, 5, and 7, what is C of n? Yep, it's just the LCM, because it needs to be divisible by all of them, but it should be the minimum number divisible by all of them, which is of course just the LCM. Yep, there's a latex fail. So we just look at them separately. First, let's look at Zn. So what can Z of n be? Remember, Z of n is the order mod 7. Yep, Z of n can be 6. It can be any divisor of 6, in fact, since we know that orders have to divide p minus 1. So there are 6 different non-zero residues mod 7. And we know that they have orders 1, 2, 3, or 6. So out of these, which ones have which order? So we actually don't need to know exactly which ones have which order, rather how many times each order appears. So we already know from our previous proof that order E is going to appear exactly 5e times. So we have 2 numbers with order 6 because 5, 6 is 2, 2 with order 3 because 5, 3 is 2, so forth. 1 with order 2 and 1 with order 1. And similarly, we can do this for mod 5, mod 3, and mod 2. So Y of n can be either 4, 2, or 1, since it has to be the divisor of 4. And these appear with frequencies 2, 1, and 1. And X of n is either 2 or 1 with frequencies 1 and 1 or 1. And Wn is always 1. So from here, note that C of n has to divide 12. So we can just do casework on the divisors of 12 and see how many times each one appears. But we can be slightly cleverer. In particular, if we look back, basically our numbers are basically all powers of 2 besides Z of n. In particular, Z of n can also be divisible by 3. But if we look at Z of n closer, the probability that something is divisible by 3 and the probability that something is divisible by 2 are actually independent, which means that we can deal with the powers of 2 and the powers of 3 dividing C of n separately. So first of all, we can deal with the powers of 3. So what's the probability that C of n is divisible by 3? If we say, take randoms n such that it's co-prime with 210. Not exactly. So it's not going to be 1/3. It's going to be 2/3, because the only place where C of n can get a factor of 3 is from Z of n. And Z of n is 6 or 3, 4 out of 6 of the times. So C of n is going to be divisible by 3 2/3 of the time. So now, how often is C of n a multiple of 4, and how often is it odd? So first, let's see, how often is it a multiple of 4? No, it can be, because y of n can be 4. In particular, the only way C of n can be a multiple of 4 is if y of n is 4. And since this occurs 2 out of 4 of the cases for y, this means that C of n is, as people have said in the chat, a multiple of 4 exactly 1/2 of the time. So how often is it odd? So C of n is odd 1/16 of the time. This is because in order for C of n to be odd, every single one of the w, x, y, and z has to be odd, which means that, so Z of n is odd with probability 1/2, y of n is odd with probability 1/4, and x is odd with probability 1/2, and wn is always 1. So C of n is a multiple of 4 with probability 1/2. C of n is odd with probability 1/16. And this means that C of n is divisible by 2, but not 4 with probability 7/16. So now, using all of this, we can now compute the expected value of C of n. The expected value of the power of 2 is going to be 1 times 1/16 plus 2 times 7/16 plus 4 times 1/2, which is equal to 47/16. And the expected value of the power of 3 is 1 times 1/3 plus 3 times 2/3. Since we said it had a 2/3 probability of being a multiple of 3 and a 1/3 probability of not. And since these two expected values are independent, we can just multiply them to get the expected value of a non-zero C. And it's 329/48. So now that we know the expected value of C, we just have to multiply by the number of possible C to get our answer. And the number of possible C is just 5 210 is equal to 48. So our answer is 329/48 times 48, which gives us 329. Are there any questions? Okay, great. So we'll move on with our next question. So this is HMMT 2014. I'll give you a few moments to read the question, and feel free to type any ideas in the chat. So has everyone finished reading the question? Great. So right off the bat, can we name some obvious M which work? Yeah, sure, 1. Can we name some class of M which work, for example? Primes is a good guess. Actually, primes do work. But in fact, we can just go ahead and say that all odds work. And the way we do this is that we want n to the n plus 1 to be equivalent to -1 mod m. So we just naively set n is equivalent to -1 mod m. As long as n plus 1 is odd, this is going to work because -1 to an odd number is -1. So when m is odd, n is equivalent to -1 mod m. So n is going to be even, which means that n plus 1 is odd. Well, n can be even. So n plus 1 can be odd, and this will work. And this doesn't work when m is even, because in that case, n has to be odd, and n plus 1 has to be even. So the construction n is equal to m minus 1 works for all odd m. So we actually only need to consider even m. So before we get into the question, we're actually going to first introduce another lemma. And this is one side of the famous Fermat's Christmas theorem, which states that any odd prime which divides x squared plus y squared, but not x and y, must be 1 mod 4. It's supposedly called the Christmas theorem because Fermat solved it while on Christmas break. Yeah, so this is only one direction of Fermat's Christmas theorem. The other direction is much harder and states that x squared plus y squared actually can be, actually states that any single number which is divisible only by odd primes 1 mod 4 and squares of primes 3 mod 4 can be written of the form x squared plus y squared. So it's an if and only if. But here we're only going to do the weak version. So yeah, we're calling it weak because the other direction is much harder. So does anybody have any ideas on how to prove this? So let's write it in terms of mod p. X squared is equivalent to -y squared mod p. And move the y squared over to get that x over y squared is equivalent to -1 mod p. So in this form, can anybody tell me something about x over y? No, x over y does not divide p minus 1. We can use the exact same trick we used for the Amy question. So we know that x over y squared is equivalent to -1 mod p. So this means that the order of x over y is 4. The reason why is x over y to the 4th is equivalent to 1 mod p. So the order has to divide 4. But it can't be 2 or 1 because x over y squared is equivalent to -1. So this means that the order has to be 4. So 4 divides p minus 1, and p is equivalent to 1 mod 4 as desired. So going back to this question, remember we only need to prove the case when m is even. So when m is even, n has to be odd because we want m to divide n to the n plus 1 plus 1. So what does this tell us about n to the n plus 1 if m is even? Well, actually, we know that since m is even, n has to be odd, which means that n plus 1 is even. So this is a perfect square. So by our lemma, if m divides n to the n plus 1, then any odd prime dividing m must be 1 mod 4. Since our lemma stated that it's either 1 mod 4 or it divides both squares, but no prime divides 1. So this means that any odd prime dividing m must be 1 mod 4. Also remember that m is divisible by 2. So any odd prime has to be less than 25. So we can just go ahead and list them out. So the primes under 25 are 5, 13, and 17. And also n to the n plus 1 is equivalent to 2 mod 4, since odd squares are 1 mod 4. So m can't be divisible by 4. So given these two constraints, we can just list out all the possible m under 50 which work. So those are 2, 10, 26, 34, and 50. So these are the only possible even m which could work, but we haven't shown that they work yet. So in order to construct it, we need n to the n plus 1 is equivalent to -1 mod p. Let's just say mod p, not mod 4. So n to the n plus 1 is n squared to the n plus 1 over 2. So we can just choose n such that n squared is equivalent to -1 mod m, and n plus 1 over 2 is odd. So the question is this always possible? Well, the second condition is just true if n is 1 mod 4. That's easy to deal with. But n squared is equivalent to -1 mod m might be a bit difficult. So actually, it doesn't really matter since we only have 5 cases. So we're guaranteed in such an n by Fermat's Christmas theorem, but there's so few candidates for m. If we're lazy, we can just go ahead and bash. So for m is equal to 2, 10, 26, 34, and 50, choose n is equal to 1, 3, 5, 13, and 7 in the respective mods. And we'll see that n squared is always -1 mod, whichever m. And n squared is -1 mod m, and n plus 1 over 2 is odd. We can guarantee this by doing Chinese remainder theorem on mod 4 and mod m over 2. So all of these cases work. And our answer is just the sum of all the odds plus the 5 evens, which we showed just work. And this is 747, so that's our answer. Are there any questions? So it looks like no. Actually, we have 2 more questions, but class is out of time. So if you have something to do, feel free to go. But if not, you can stick around and Brian will present the last 2 questions.
All right. So here's the next question. I'll give you guys a bit to read it and think about it, and then we'll be going over it. Also, if you have ideas, feel free to send them in the chat. All right, so I guess the first thing we can do is we can try to, well, we can first replace 2013 M with big M so that it's just easier to work with. So that's gonna be the first thing that we do. And then, so we want to characterize also big M. So, well, how do we go about doing that? Well, for example, we would, we want to consider when big M divides things, right? But so this is easier to deal with if we just consider any prime power divisor of big M, right? So we consider any prime power divisor of big M. And then, so what does this problem mean in terms of, what does this problem mean in terms of like what we want, right? Well, basically, oops, that's the wrong, hold on. Okay, so we basically want, we know that if the order divides n, which is basically what it means for big M to divide n to the n minus 1, then we want the order to equal 1, right? So what do we already have? Well, so we want to determine some property of the order, right? But we know that one of the properties of the order is that it divides the phi function, right? So yeah, that's just the phi function evaluated at p to the k. And well, now how do we combine these two conditions that we want in order to get that the order equals 1, right? Well, if we just had that their GCD was equal to 1, that'd be enough. And then because if we have that something divides two relatively prime things, then it clearly can only be 1, right? So, well, we already know that n is relatively prime to big M, and so that means that n is relatively prime to p, right? So now, basically, we want it so that the GCD of p minus 1 and n has to be 1, but we remember that if basically the GCD of big M and n is 1, so basically if anything that divides p minus 1 also divided big M, then that'd be enough, right? Because then they can't have any prime divisors in common, right? So that's a condition that's sufficient, but we actually want to show that that's necessary, right? So basically, how are we going to go about doing this, right? We're basically just going to suppose, let's say we had a big M that didn't satisfy this, right? Like there's P and Q that basically break it. Well, now what? Well, basically, we want to provide a counterexample then. We want to construct an n such that big M divides n to the n minus 1, but big M does not divide n minus 1. Right, so well, basically the way we would go about doing this is, well, to deal with like most of the prime divisors, we just let it be 1 mod everything that isn't like mod big M over p to the k. So then we only have to worry about like the p to the k. So, well, now we basically need to find an A such that A is not 1. I'm supposed to say A is not congruent to 1 mod p to the k. But A to the q has to be congruent to 1 mod p to the k. Right? So now what this means is, so this, we see that this would be nice because basically we could let n be congruent to A and then it basically just works, right? But now how would we find an A? Well, basically we consider a primitive root, right? And we remember that like a primitive root is basically a root thing that's order p minus 1, right? And now we claim that if we raise it to this power, then it works, right? And we see that this works because basically if we take that to the q, then that's essentially raising g to the phi of p to the k power. And then that's clearly 1 mod p to the k. While if we take it as is, then it's clear that it's not a 1 mod p because g is a primitive root and we're not raising it to any multiple of p minus 1, right? So A satisfies the properties that we want, and now we just put everything together, right? We let n be congruent to A mod p to the k, and we let n be 0 mod q. And then we see that we can combine these because all of the moduli are relatively prime because we have that q does not divide m. Right, so then this is sufficient to show that our counterexample works. So then we basically proven what we want, right? So so now what? Well, now we have to solve the problem, right? We remember that like big M is a multiple of 2013, and so now we have to factor big M. Right, so the slides kind of got cut off, but basically we just apply the property that we just found, and to show that basically 10 has to divide little m, and then we basically see that because little m is between 1 and 300, we just try them all, and then all of them should work except for 290. But this is just like this is the easy part, the like computational part of the problem. The important part was mostly finding this key lemma. Basically 290 doesn't work because it's a multiple of 29. And then basically what the property that we found was basically if we have p divides it, where here p is 29, then for any prime multiple of p minus 1, that also has to divide it. But here we see that 7 is a multiple of 20. 7 is the divisor of 28. But 7 does not divide it. So then that's why 290 doesn't work. Right. So here we basically have we have the rest of the computation, right? And then so we got our final answer is 4,360. All right. So are there any questions on that? If not, we'll move on to our last question of the day. So our last question of the day is this, and then I'll give you guys a bit to read it, and then we'll be going over it shortly. All right, so basically what we want to do is, well, first we're gonna be dealing with some edge cases, right? So we first consider the case of what if P equals Q, right? So this case is significant because otherwise if P didn't equal Q, then we could just consider the two conditions, P divides 5 to the P plus 5 to the Q, and Q divides it separately. Whereas if P equals Q, then P squared dividing something is different, right? So if we have P squared divides 2 times 5 to the P, well, then we see that 2 times 5 to the P only has 2 prime divisors, right? It only has divisors of 2 and 5. So that means that P can only be either 2 or 5, but we see that it's also not a multiple of 4. So yeah, exactly. We need P equals Q equals 5, right? So now we consider our other case of P doesn't equal Q, right? Now we're gonna consider more cases, such as basically what if Q equals 5, right? Because when one of them equals 5, then for example, Q dividing the right is clearly true, right? So now we just need P to divide it, right? But so now we recall that by Fermat's little theorem, 5 to the P is equivalent to 5 mod P, right? So then we just replace 5 to the P with 5, and then we get P divides 5 to the 5 plus 5. So then we just calculate 5 to the 5 plus 5, and that's 3,130. And then we have that P is either 2 or 313, because remember, P doesn't equal Q, so P is not 5 here. So then we get our 4 solutions, right? Because we could have either let Q equal 5, or we also could have let P equals 5, which is where we get our other 2 solutions from, right? So now we consider what if neither of them are 5, right? Well, another special case is when, well, what if one of them is 2, right? And this is important for reasons we'll see later, but basically if one of them is 2, we can do some pretty similar reasoning where 2 clearly divides the right-hand side because you're adding 2 odd numbers. So then we just need P to divide it, and then we reduce 5 to the P into 5 again, and then we get P equals 3. Right, so then this gives us 2 other pairs. And then so now we end up with our final case of what if they're different and not equal to 2 or 5? Right, well, now what? Well, basically, we suppose we have p divides 5 to the p plus 5 to the q again. And well, we can reduce 5 to the p into 5 again. And we can take out a factor of 5 because we know that p isn't 5, right? So now we're going to be defining something called v2, right? So v2 of a number n is the largest. You can think about it as basically how many times does 2 divide a number, right? So for example, like v2 of 4 would be 2, v2 of 12 would also be 2. And the reason this is significant is because, well, basically, we have that because the order of 5 mod p divides q minus 1, no, divides 2 times q minus 1, but it doesn't divide q minus 1. This basically tells us that it has to basically, if what we think about as happening is when we add another factor of 2 onto q minus 1, the order goes from not dividing it into dividing it. So now what this means is basically they have to have the same power of 2 dividing them, or else that wouldn't happen any other way, right? Because no other prime factors are changing. So now basically this tells you that the v2 of the order is equal to the v2 of 2 times q minus 1. But we remember that the order also divides p minus 1. So then v2 is at most the v2 of p minus 1. Right, and well, basically, and so this is why we needed p and q to be odd, by the way, because otherwise we could not have done this, because otherwise, if like plus 1 and minus 1 would have been equivalent, right? So that's why we needed it to be odd. But now that we're in this case, we see that we have this inequality, but we also know that p and q are symmetric, right? So we can come up with the same inequality with swapped variables. And then this is enough to solve the problem, because basically now we get this contradiction of these two inequalities can't both be true at the same time, right? So that's enough to finish this last case. So then we just put together all of our solutions that we found, and then that's our answer. All right, so I think that will be all for today. And then, yeah, because we're going quite late today, but